this group. I'm really excited for today's CLE. We kind of have a dream team of experts here from Exponent today. I'm going to, do some brief introductions and then I will just hand it over to our speakers. I think our speakers' biographies could probably take up the full hour. I'm just going to go off and hit the high points and very well educated, well qualified. We have Dr. Erin Murphy. She's a managing scientist at Exponent. Her work focuses on polymer science and material chemistry. She has a Bachelor of Science degree in chemistry and biochemistry from Cal Polytechnic State University and a master's and PhD in chemistry from UCLA. Prior to joining Exponent, she worked for 7 years in private practice where she focused on research and technical roles. She's an expert on a wide variety of materials, including, I found this out, self-healing materials. So maybe if we have a few minutes today, she can talk a little bit about that. We also have Dr. Michael Dimitriou. He's a senior manager at Exponent, where he focuses on polymer science and material chemistry. He has a Bachelor of Science in Material Science and Engineering from MIT, and a PhD in Materials Engineering from Cal. He specializes in the design, manufacture, and performance of polymers in a variety of fields, including biomedical, electronic, building, and construction. And then we have Dr. Matt Radlinski. He's a senior managing engineer at Exponent in the Building and Structures Division. He earned his Master's of Science in Civil Engineering in Poland, and he has a PhD in Civil Engineering from Purdue University. He specializes in concrete and cement-based materials. He handles claims involving all aspects of construction, including installation deficiencies, material failures, and performance concerns in a wide variety of applications. So needless to say, we have a well-credentialed and excellent panel today. So I look forward to passing it over to them and they can educate us a little bit about plastics and construction. Thank you so much.
Great. Well, thank you, Jameson, for that very lovely intro and the nice words. And thank you all for, especially with the snowstorm, the ice storm, excuse me, and the challenges you guys are facing. We appreciate the invitation. We're excited to talk to you today. You see our title. We want to talk to you about the future is plastics. So all of the plastics and polymer materials that have been coming into the building industry and let you know a little bit about what plastics are, what polymers are, how they can be used in this industry, and really what are the common failure mechanisms and what we see when we've been out there, our experiences, and what you can take from that and how that can help. So I will ask Mike to move forward. And you've just heard all about me, so I don't need to dwell on this. I will tell you that most of my work at Exponent does involve litigation support. About 70% of that, a lot of that is in construction defect. I do some product liability and intellectual property work as well. On the proactive side, a lot of it is also in building and construction, some medical device work, and some consumer product work. So what are you going to hear today? Today, we're hoping to tell you a bit about what polymers are, give you a very high-level Polymer 101 crash course. Once you understand the chemistry and properties of polymers, we're going to tell you why they're useful in building and constructions. So all the different types of applications, how they can be used in piping, windows, flooring, and then some of the factors that affect their performance. So that could be the formulation of these, how they're installed, how they're manufactured, what are their end use conditions, and then some litigation case studies about these polymers in these applications and how they failed and why we see them fail. Is it formulating issues? Is it installation? And then some of the characterization techniques that we use to form our opinions and how do we evaluate the performance and the failure mode of these materials. But why do we care? We care because polymers are everywhere. If you look around, there's polymers in almost every application space and in every industry. So this ranges from biomedical to aerospace, and of course, construction, they're everywhere. So these polymers can come in many forms. We can get bulk polymers, so you can think about your plastic piping to transport water. You can get composites. So that's going to be if you have, say, fiber reinforced epoxy, that's a composite material. You can get films like your packaging materials. You can get paints and coatings that go on your tanks. You can get adhesives and sealants that need to have a barrier property. All of these are polymers in some form of another. Next slide, please. So in the grand scheme of things, they're always designed to work perfectly. We think about the end use conditions when we design the polymer and the formulation. We think about how long does it need to last in this application. We validate it, we test it, we pull on it and push on it in the way we think it's going to be stressed in the application. And we look at all the quality control that we need to put in the manufacturing process to ensure that we've met the performance spec. But there's a lot of factors that are outside our control. So something goes wrong in manufacturing, or somebody value engineers a component out of the system. There's a lot of places in the supply chain where communication can break down. Somebody can install it wrong, or somebody didn't consider an environmental factor when they spec'd that product in. So even though we designed everything to work perfectly, sometimes things can still fail. Next slide. And that's what we end up seeing. So these products are designed perfectly, but something goes wrong, whether that's manufacturing, whether that's overload the system, it wasn't designed properly, or some combination thereof. And that's where we get called in, and that's where we end up having a lot of fun. So today we're gonna split this talk up into a few sections. I'm gonna start out and I'm gonna give you that high level Polymer 101. I promise to not make it too painful. There will not be a test, but we're gonna tell you a little bit about all those tools in our polymer chemistry toolbox to give you the properties and function you need in application. Then I'm going to hand it over to Mike, and he's going to tell you about some of those common failure modes and give you some case studies to teach you that. So some plasticizer migration and environmental degradation and some sealant materials. And then Matt's going to finish us off with some applications in concrete, flooring, and tile. So some of these application spaces where you just need a little bit of polymer, but if you mess that up, it can have catastrophic effects. So let's start out with Polymer 101. So starting off with, what is a polymer? Well, a polymer starts out with a monomer, which is just a single unit of something. And when you link all of those monomers together, you build up what's called a polymer. If you link up one monomer with another monomer, you get what's called a dimer. Put 3 of them together, it's called a trimer, and you can keep building. If you only have, say, less than 10 units together, we call that an oligomer. It's just a small kind of in-between material. But once you get past 10 repeat units, we call that a polymer. And that can go on from, we like to say, 10,000 molecular weight up to over 1 million molecular weight. So these can be very large molecules. There's different ways you can build these. So I've got a couple of the mechanisms up there. Basically, you can add the polymer to just the growing end of the chain. You can have multiple chains come together. And the important thing is there, for us polymer chemists, there's different kinetics and therefore different properties at the end of the day, depending on which polymer mechanism you choose to employ. So depending on how we go about making these giant structures, we can get different properties therefore. Also, the type of chemistry is going to be very important. So there's a whole lot of different individual monomer building blocks that we can choose to build our polymers out of. So we've got a few up here on the top. The top are the monomer units. So ethylene is a monomer, tetrafluoroethylene is a monomer, and so on and so forth. And by changing out the chemistry of that monomer unit, we put that different functionality into the polymer backbone. So as we polymerize it from ethylene monomer, we get polyethylene. From the tetrafluorine ethylene monomer, we polymerize that to polytetrafluoroethylene, or PTFE, and so on. And so as we control the chemistry in the backbone, that then imparts different functionality. So for that fluorine group, that makes it very hydrophobic. It no longer will attract water, water will be repelled. And so that gives us the functionality that we apply to nonstick coatings or nonstick surfaces. Same for silicon. So silicon ends up being a very high temperature, high chemical resistance. It's also very soft and flexible. Ends up being used in a lot of biomedical applications. Lactic acid, that's something that is unstable in water, so it can be degraded in the presence of water. So by knowing the different chemistry and what it imparts, we can choose the different types of polymers and plastics for the application. Next slide, please. There is a lot on this slide, but this is considered your cheat sheet to polymers. So we break them up into multiple classes. So you can look, and I think one of the real world applications is when you see your recycling logo on the bottom of your plastics and you get a number, 1, 2, 3, 4, 5. That breaks it up into these categories. And you may see things like PET or PS or PC. Those are those abbreviations for what those polymers are. So the different classes, we can have thermoplastic polymers. Those are typically recyclable. Those are these that you'll have your recycling logo on. And that means that you can melt them and reprocess them multiple times. Versus a thermoset, this is something where you have chemical crosslinks forming into a three-dimensional network. Those crosslinks can't be reversed, so it is a non-recyclable system, but that also tends to mean that it's a very strong, stiff, high thermal stability material. So this is your epoxies and your phenolic resins. You can also have rubbers or elastomers. So these are your very stretchy, flexible materials. These tend to be used in gaskets, in sealants, things like that. And then you can have something that has properties of both, which is a thermoplastic elastomer. So it's temperature dependent. It can be plastic under certain conditions and elastomeric under certain conditions. So as you can see, we can change the chemistry and we can get this huge wide property set of plastics to rubber and somewhere in between. Please ask questions along the way if you guys have them. Otherwise, we'll keep cruising through. One other thing to keep in mind, besides just the chemistry and how we build that, we can also create different architecture. So we can make it a branched system, or we can make what's called a dendrimer, which is shown here in the center. So depending on how we build that polymer chain, we'll get different properties as well. We can link them together like we talked about, and depending on this structure, that will give us different properties. And so that's what we talk about when we say structure-property relationship. We know that if we change the structure, we can tune the properties. Another way of getting that is by how we control those monomers. You can use multiple types of monomers, and if you put them in sequence, so either alternating like we're showing here, red, blue, or in blocks, you'll get different performance properties. So again, by controlling how we place those monomers in sequence and the overall architecture of them, we can control properties. So one good example, this is from my former company. You can have just a few monomers and a few different architectures, and you can get to a lot of different combination of polymers and commercial products. So Kraton was my former company. We made styrenic block copolymers. And in 2011, we had 73 commercial products. These all started from 3 monomer building blocks. So those are the 3 monomers. So just 3 starting building blocks, but by changing the molecular weight, the architecture, the length of these building blocks, the ratios of styrene to rubber, the degree of branching, we could get all of these different products that all had different properties and all went into different applications. And so it was something that was really amazing to me as a polymer chemist. You just have a simple set of building blocks, but you could have an entire business in multiple business lines. These products went into things like repaving the Indy 500 racetrack to adhesives and baby diapers. So they go all over the place. So we can change structure to get properties, and these properties include things like the viscosity or rheology. So how does it flow as a function of stress applied? How strong is it? So is it elastic and stretchy, or is it plastic and it's going to snap on you? And how well does it hold stress over time? So is it something that it can undergo multiple cycles of stress? Or is it something that when you apply stress and hold it, it's going to slowly creep over time? So this is something that we need to understand about our materials. And so we can measure the properties on, and different polymers, plastics versus rubbers, for instance, will have different set of properties and respond to stress different. So with that, now we know we have plastics, rubbers, thermosets. We have all these different types at our disposal. We know we can choose them for different applications. There's lots of different places in buildings and structures that we can place these materials. They can go into decking and flooring and in coatings and paints and sealants and some of the places we've talked about. And you can see over on the right some of these figures that 9% of plastic production worldwide goes into the building and construction market. And Exponent does have direct experience with almost every type of polymer you can imagine in building and construction, whether that's in litigation support, insurance support, or in proactive. And the motivation behind bringing in polymers is that they are often cheaper, they're lightweight, they're easier to install, and you can get a lot of different surface finishes on these by just molding them in, so they can be aesthetically pleasing. The selection of these is not necessarily straightforward though, because a lot of times they have different compatibility issues with what they might be exposed to in their environment that you wouldn't think about with your more traditional construction materials. There's additives and fillers that could migrate from one material to another. Manufacturing also plays a big role in the performance of these. You may have old technology that switched over and it could change the properties. And installation, as we've mentioned, has a big role to play in the performance long term. So real quick, I'm going to tell you a little bit about some bulk polymer fracture and failure that we've seen in construction. So one of the main places that you see plastic in construction is in piping and used to transport water. So the bottom left, this orange piping is a fire sprinkler pipe. We do see a lot of failure there. In the top right, that is CPVC. So that's just non-potable water piping. And then on the bottom right, that's actually an elastomer that is fractured. So that's a embrittled seal that is fractured. But what we do when we look at these, we need to first understand what does the environment look like that this was in, and inspect the evidence to see, was it a manufacturing defect, or do we think it was installed improperly, or was there some end use condition that may have impacted that failure? So we look to see for manufacturing defects, is there something obvious? Was it along a weld line that it failed? Was there a big void? Was there a fisheye, which is an unmelted polymer particle? Is there something in there that initiated the stress and the failure? If not, is there something that is obvious from installation? Or is there an environmental stress? Is there an impact mark? Is there signs of chemical contamination? Is there something else that might have impacted that failure? And a lot of times that's what we see, that it could be combinations of the two. We could see an impact event along with some chemical stressors, and that's how we will chase that failure. I think that's it for my high level polymer chemistry. So hopefully you guys have a good foundation of the different classes of polymers, the different types of chemistry involved, and I will hand it over to Mike.
Thanks, Erin, and thanks everybody for tuning in. So what Erin hopefully demonstrated in that last slide is there are a lot of ways that these construction materials can potentially fail. And what we wanted to do is take a little time to walk you through two relatively common root causes for failure that we typically or see more frequently in our line of work. But before that, a quick introduction, and thanks to Jamison for already doing half of this for me. But my background is similar to Erin's in the sense that I'm a material scientist with a focus on polymers, structure, property, and processing relationships. And like Erin, about 2/3 of my work is really focused on reactive work, where I work with polymer failure analysis. And I do a good deal of intellectual property work as well. The remaining third is reactive, where I have direct relationships with manufacturers and corporations, helping them with product development. So the first mechanism of failure I wanted to talk to you all about is referred to as plasticizer migration. And before I describe that, I wanted to take a brief moment to explain to you all what plasticizers are. So plasticizers are materials that are added in varying amounts to polymers. They are small molecules that are essentially mixed into polymers to provide increased flexibility. And they do this by essentially lubricating the space between polymer chains. So if you look at the image on the right, that kind of depicts what's happening. In the top right, you see essentially an entanglement of polymer chains. And by adding plasticizer to that entanglement, you're kind of increasing the space between them and allowing those chains to slide over themselves, giving you, as a bulk material property, more flexibility. A good analogy might be your spaghetti, right? If you cook some spaghetti and don't throw any oil or sauce in immediately, it's all clumped and stuck together. But by adding butter or tomato sauce, you start to add that lubrication that allows things to flow, and the spaghetti essentially becomes more movable. That translates to higher flexibility and bulk properties. And this is not a novel concept or technology. Plasticizers have been around for a very long time, and they're typically used in most applications in construction. Examples might be paint, wire insulations, and sealants. So to highlight the effects of plasticizer, just to give you a general sense of what I'm talking about, an easy example is polyvinyl chloride, or PVC. What you can see at the top is one form of PVC where plasticizer, or at least more plasticizer, has been added. And you can get things like shower curtains or inflatable pools, where these materials have an increased amount of flexibility. On the flip side, if you are to remove plasticizer and only have that PVC, or have a reduced amount of plasticizer, you get a material that's significantly more rigid and stiff, like piping and or gutters. So back to plasticizer migration. As a formulator engineer, when you put a plasticizer in a polymer, what you essentially want it to do is stay in that polymer. You want it to stay in place, and you want it to do or keep the material as flexible as it was the day it came off the production line. Unfortunately, that is not always the case. Plasticizers are known to be able to actually migrate when a material containing plasticizer is in contact with a neighboring polymer. So the simple depiction on the left, what you can see is, a depiction on the right, what you can see is the polymer on the left is formulated to contain some amount of plasticizer. And when put in contact or close to a neighboring polymer, over time, what might happen is some of that polymer migrates into the neighboring polymer. And unfortunately, this kind of has a double negative effect. You get a change in properties of the host polymer that is losing plasticizer, and you also get a change in properties of the neighboring polymer that is gaining plasticizer. The host polymer, by losing plasticizer, may demonstrate a loss of flexibility and or a loss of adhesion, while the neighboring polymer, which was originally made to not be flexible or not contain plasticizer, is now possibly experiencing a reduction in viscosity, may be susceptible to environmental stress cracking, and it may be becoming more flexible than originally intended. So to give you a more tangible example of this, one way of thinking about it is simply drying mud. Mud would be dirt mixed with water, where you could imagine water is your plasticizer. And over time, as water begins to evaporate, the analogy would be you're losing plasticizer from your material. And what you end up with is going from a flexible material that's possibly stickier and better at demonstrating adhesion to something that is brittle and less flexible. A more practical example of this in the construction space might be caulking or sealants. You can see in the bottom left image, there's some caulking that's used to apply to a window joint. It's flowable, but once it dries, it is a material that needs to demonstrate a certain amount of flexibility and adhere to those substrates. However, over time, if that plasticizer leaves the sealant, you could end up a situation where it embrittles, it possibly delaminates, and it no longer serves its function as filling in that gap and sealing that gap. So this was an example of what happens to your host polymer when plasticizer leaves it. The other side of the equation is, where is the plasticizer going? And what I have here is a staged photo of a potential scenario where this could be a problem. So what you're seeing is the orange pipe, which is similar to what Erin introduced earlier, is CPVC. This is piping typically used for transporting non-potable water. It's also used for sprinkler pipe applications. And this is a relatively rigid material that does not contain substantial amounts of plasticizer. In a given scenario, you may have a situation where cables or wiring becomes in contact with CPVC. And in the left image, what you can see is there is contact right at the top of this pipe. And the cable or wiring, which has insulation that is flexible, typically contains a good deal of plasticizer. And now you have introduced a route for plasticizer to migrate from the cable into the CPVC. Now, it turns out CPVC is susceptible to a form of cracking referred to as environmental stress cracking. This is a cracking that requires two components or actions to cause the material to crack. One is stress. It needs to be under some form of pressure from the water source or bending from some other external push-pull mechanism. And it also needs to be exposed to some type of solvent that could be a plasticizer. So under certain conditions, this is a scenario where you may in fact end up with plasticizer going into the CPVC and initiating some form of environmental stress cracking. And to give you an example, here is a CPVC pipe that we are looking at it in the top image from the outside, the outer diameter of the pipe. This would be what you would see standing next to the pipe in use. And what you can see is in a long jagged crack along the length of the pipe that has started to grow. And what has happened in this situation is you see this black residue that in fact contains polymer due to contact with another material that contained plasticizer. And this has initiated a crack due to environmental stress cracking. And this crack has in fact propagated all the way through to the inner diameter, which of course is undesirable for any sort of pipe application. With sufficient pressure or time, this crack may expand and may eventually lead to a rupture of this pipe. So that was one mechanism that I would say we commonly see at Exponent that is initiated by some form of migrating species or plasticizer migration. The other mechanism that I wanted to go through is environmental degradation. So what I mean by environmental degradation is the degradation of polymers due to exposure on environmental factors that you would expect in construction applications. What these might be would be thermal fluctuations. This could be humidity exposure, could be fluctuating stresses due to the application, or it could be exposure to sunlight or ultraviolet radiation. Those are typically the more common environmental stressors, but there can be others. For example, if you're next to the ocean, salt exposure from the ocean may be a possible stressor. To highlight this, I was going to take the example of IGUs, or insulating glass units. So in their simplest form, IGUs are two panes of glass separated by an interstitial space. And they can be used in residential as well as construction applications, or in residence or construction or commercial buildings. And to achieve the interstitial space, essentially what you get, or what you do, is you put a spacer bar around the outer perimeter, which holds your two panes of glass apart. The spacer bar can sometimes contain desiccant, which keeps your inner atmosphere void of any moisture. And then to lock everything in place, you need to provide a sealant that holds everything together and keeps the the interstitial space sealed. In some IGU constructs, this is typically achieved by doing it with two sealants, a primary sealant and a secondary sealant. And the reason being, both sealants provide you with a different function, which in combination gets you to your IGU function. The primary sealant is added because it has excellent barrier properties. It essentially stops any gas or moisture from moving in or out of this interstitial space. And that's something you want. The last thing you want is moisture to come inside between your two panes of glass, to condense and onto a surface and be something that you can't access to clean. The disadvantage of primary sealants typically is they don't provide enough structural support. So you need to add a secondary sealant that really locks things in place and gives you that structural support. Here's another example of what this might look like from a cross section. You can see this is the edge of an IGU, where this black section or black layer here is your secondary sealant, locking everything in place. But because it doesn't necessarily have the best barrier properties, you add a second sealant right next to it that is able to sustain any sort of blockage and not allow anything to pass in and out of the window, keeping it dry and clean. Now you can imagine, in addition to those properties, structural support and being a barrier, there are additional requirements we have on sealants. And I've listed a few general commonly needed requirements for such applications. So you obviously need these materials to be adhesive and demonstrate some sort of tack. You want them to stay stuck between the spacer bars and the glass surfaces. If things unstick, they will generate avenues or pathways for gas or moisture to pass through. Like Erin had mentioned earlier in this talk, your materials need some level of elasticity and strength to work under the operating conditions you need them to operate under. I'd already mentioned how barrier properties are necessary so that moisture can't get into that interstitial space. You need them to remain stable to operate sufficiently throughout the function of their lifetime. And in a lot of these situations, if they're going on high rises and you're looking for a very pretty curtain wall, you need the sealants to aesthetically fit into the broader construct. What might not be as obvious as what I've added here is flow or reactivity. There are certain short-term demands that aren't necessarily focused on during the final product. So as you can imagine, during production, you need to manipulate these sealants to get them sufficiently into place. And that may require you to increase temperature to get them to flow, or it may be an unreacted material that you apply and then it slowly cures to solidify and lock everything in place. So what you should all make sure is highlighted here, what I should highlight here is that environmental degradation may and probably will have a different impact on all these properties. And depending on how these properties manifest or change throughout the lifetime of an IGU may result in an eventual different failure. And to highlight that, I'll just go through two examples. So if we're to refer to barrier, like I said earlier, what do you need a barrier to do? You need it to block the passage of fluids through the surface or joints of openings in a material. If the material is to degrade such a way where you no longer get those barrier properties, you would end up in a situation depicted by the photos here. You may get fogging on the inside of the window or condensation of moisture. And unfortunately, the reality in these situations is you can't clean it. You need to replace these IGUs because you are not able to access those inner surfaces of these IGUs. To give you another example, let's look at stability. So there are a lot of ways you can interpret or a lot of meanings for the term stability when it comes to materials, but to take it in its simplest form, you need the sealant to stay where it is. If it is not stable and it doesn't stay where it is, you may end up with a situation depicted by the image on the right. So what you can see here is the top edge of an IGU, where the primary sealant has actually started to flow down the inner pane or the inner surface of one of the panes of glass. And this for one, is not aesthetically pleasing. And for two, may end up in a situation where you compromise that barrier and do in fact allow some form of moisture or air to get into that interstitial space. So on a first pass, in looking at this, going back to my earlier example, without any additional testing and only this visual observation, a scientist may see this and say that this could be a result of environmental degradation, but it could also be a result of plasticizer migration. Like I said earlier, plasticizer migration can reduce viscosity and it can increase the flowability of materials. And I think it's clear to say from this image that this material that is starting to drip down a glass pane is in fact showing more flowability than you might expect. So what you require in situations like this is some form of testing to figure out what is going on. So you can deconstruct these windows, harvest this sealant, and perform a number of tests to determine what is the root cause. So I've broken it up into kind of three simple concepts here. So what you can see both visually, but through some sort of rheological testing, is that this material is showing a reduction in viscosity. And this can be caused by both environmental degradation or plasticizer migration. But by doing or performing a combination of two additional chemical analysis, by you can back out what the governing root cause is. So by performing chemical analysis to search for plasticizers, if you're able to show the lack of plasticizers in this material, that is an indication that there is possibly no plasticizer migration happening. And concurrently, if that's the case, what is likely causing a reduction, an increase in flowability, is a reduction in molecular weight. This comes back to what Erin was talking about earlier with regards to the length of polymer chains. As you go from monomer to dimer to trimer to oligomer to polymer, the definition of polymer encompasses lots of different lengths. And GPC allows you to characterize the length of that polymer chain. And one form of environmental degradation to polymers is a reduction in that polymer length, which leads to increased flowability. So in conclusion, by being able to perform these tests and essentially break it into this simple grid, it's a simple example of how you may be able to elucidate through testing if the mechanism of this failure is through environmental degradation or plasticizer migration. So with that, I'm going to pass it over to Matt, and thanks for your time.
All right, thanks, Mike. Can everybody hear me? Can anybody hear me? All right, thank you. Good afternoon, everyone. Again, my name is Matt Radlinski. Thanks so much for this opportunity to speak to you about these exciting topics. What I'd like to do is, given my background, I wanted to sort of transition from, the kind of the examples of bulk use of polymers and plastics in construction. You just heard Erin, Mike talk about sealants, window applications, plastic piping, and so forth, to perhaps less obvious, but nonetheless extremely common and frankly crucial polymer applications in construction, specifically in concrete materials and construction tile and flooring applications. Again, Jameson did an excellent job introducing us. I'll just briefly mention, unlike Mike and Erin, who are polymer scientists, I'm a civil engineer. I have my master's in structural engineering and PhD in concrete materials and technology. I would say over the last 12 years at Exponent, I've been at Exponent. I've been spending roughly 3/4 of my time or effort on reactive cases and the reactive side of things, primarily litigation cases with smaller fraction of non-litigation insurance work, focusing on investigating concrete materials and concrete construction issues, as well as a variety of cement-based materials, things like stucco, tile thinset, flooring underlayment, cement fiber siding, pool plaster, etc. And then the remaining 25% or so has been dedicated to things like condition assessment and remaining service life analysis for concrete structures and piping. Next slide, Mike. Thank you. So you may still be wondering, why is a concrete guy going to be talking to you about plastics and polymers? Erin, I think, already answered that question, which is basically that because polymers are used everywhere, as you'll see here in a moment, we put polymers in the concrete mixture, we embed them in concrete, we apply them to the concrete surface, and then put them under the concrete, and same goes for flooring and tile applications. So next slide, Mike. Just jumping right into the polymer applications in concrete materials, and specifically chemical admixtures. Concrete today is not what the semi-random mixture of some rocks, sand, cement, and water used to be 50 or 100 years ago. It's a far more sophisticated and generally highly engineered material that's sort of customized for a given application. In vast majority of cases, any concrete truck leaving a ready-mix concrete plant, in this country at least, heading over to a commercial construction site, will incorporate one, if not multiple, chemical admixtures. And as you could guess, the vast majority of these chemical admixtures are polymers, either in a liquid form or powders. Each one is responsible or controls or enhances totally different property of concrete, either in its fresh state or hardened state. We have air entraining admixtures that introduce microscopic size air bubbles that help control or improve resistance of the concrete to freezing and thawing. We have water reducing or plasticizing admixtures that allow for improved workability of concrete during placement. We have set retarding admixtures that are commonly used in hot weather applications. Set accelerating admixtures, obviously opposite in cold weather placements, and a variety of specialty admixtures such as corrosion inhibitors, shrinkage reducing admixtures, viscosity modifying agents commonly used in self-consolidating concrete. These days, we can even make completely waterproof concrete, which obviously by nature is rather porous and permeable, thanks to integral waterproofing admixtures. There are also anti-freeze admixtures and a variety of coloring admixtures used in decorative concrete applications. Next slide. Polymers are also extremely common in concrete reinforcement applications. You must have all seen the green colored rebar, either in an active construction site or lying somewhere along the side of the road. Being constructed, commonly used as an epoxy coating on reinforcement, obviously to increase resistance to corrosion, particularly in transportation structures, bridges, pavements, etc. Similarly, in post-tensioned concrete applications, plastics are used as sheathings for the pre-stressing tendons. Over the last decade or so, more and more commonly, at least I have seen, and I'm sure it's getting more and more popularity in general, the use of fiberglass reinforcement, which looks identically, I would say, to a regular rebar, almost impossible to tell apart, other than even has the same type and spacing of the ribs, with the obvious advantage of it being non-corrosive. Lastly, fiber reinforcement, most common type including polypropylene fibers. generally used as a secondary type of reinforcement in concrete to improve ductility and resistance to cracking, but sometimes used as solely as as the only reinforcement in shotcrete or gunite applications. We have a whole host of polymer-based concrete curing products, anything from polyethylene sheeting used to retain moisture in freshly placed concrete and minimize the drying during the curing period. Liquid applied or I guess spray applied white pigmented curing compounds, extremely common in concrete flatwork, slabs, and grade and pavements. Similar products called evaporation retardants, used generally in hot weather concreting in hot and windy conditions to minimize the risk of plastic shrinkage cracking, like you can see in the photo on the right hand side. Next slide. Then we have a group, of course, of a variety of coatings that is commonly installed on concrete surfaces. Traffic coatings in parking garages, things like epoxy and urethane coatings in plaza decks, sports coatings, basketball and tennis courts, chemically resistant coatings in food and beverage facilities, and of course decorative coatings in showrooms and miscellaneous residential and commercial decorative applications. Next slide. Essentially, almost all, if not all, waterproofing products, concrete waterproofing products, are polymers. Things like waterproofing membranes, both positive and negative side, liners in the concrete pipe and tanks, and PVC water stops installed in applications of concrete construction joints during an active concrete construction project. Mike has sort of provided an example of an environmental degradation of polymers in a window sealant example. I sort of wanted to provide a somewhat comparable example, but obviously in a concrete application, where we're looking at a apparent degradation of a concrete waterproofing membrane. In this particular case, it is a blindside waterproofing membrane. It's installed on concrete shoring prior to placement of the concrete, and which in this case is roughly a 2 foot thick concrete wall in a below grade multi-story parking garage underneath a high-rise building. And next slide, please. If you were to take a look in the parking garage, that's what you would see. Many locations of water intrusion through cracks and joints through the concrete. Certainly not a condition you would expect of a fully waterproofed brand new concrete structure. As we've discovered in the course of our investigation, which involved sampling of the water at these water intrusion locations, chemical analysis of those samples, and comparison to the results of chemical analysis of the waterproofing membrane, both sampled from the building and in its unused condition. Next slide, please. We determined that there was clear evidence of chemical degradation of the waterproofing membrane products, likely associated with certain chemicals present in the groundwater in that particular area. So we've observed clear evidence of many compounds, chemical compounds, leaching out of these waterproofing membrane into the water that sort of flows through the wall and sort of leaches these compounds out of the compound. Of course, we were never able to conclusively determine if that was the sole cause of the water intrusion, and whether or not there were any other issues related to the installation and lapping at seams and so forth. But certainly it was very clear evidence that despite the fairly recent installation, there certainly has been a fair amount of degradation. Next slide. Moving on to a family of concrete repair products. You know, these days, short of in repair situations, concrete repair situations, short of replacing concrete with new concrete or at least some sort of cement-based grout, I would say the majority, if not all, concrete repair products are polymers. Things like coatings that I've already covered, and sealers, a variety of crack repair products, ranging from extremely low viscosity methacrylate sealants that are spread on the surface of concrete flatwork, particularly bridge decks and pavements, to seal hairline cracks, polyurethane flexible sealants used to seal joints in route and seal type of repair, epoxy injection used to seal the cracks, number one, and number two, structurally bond and restore structural capacity of the concrete, as well as urethane grout used to seal leaking cracks. But also instances of use of polyurethane foam that expands roughly 7 times and does a great job of lifting, settling slabs and filling voids below slabs in grade. And polymers such as epoxy resins are also commonly used to bond carbon fiber reinforcement in repair and strengthening applications. Now shifting gears into examples of polymer applications in the flooring industry. I probably don't have to tell you how common polymer flooring, or polymer-based flooring, I guess, is in commercial applications, including school, medical facilities, offices, etc. Products such as sheet vinyl, vinyl composition tile, luxury vinyl tile, more recently sort of being extremely popular in residential applications as well, and rubber flooring, carpets, etc. As you could guess, all these products are also typically bonded to concrete with a polymeric adhesive, typically an acrylic-based or an epoxy-based adhesive. We put moisture vapor retarders, commonly referred to as visqueen, to minimize the underneath the concrete slabs on grade, to minimize the risk of moisture vapor transmission through the slabs and moisture damage to concrete, to moisture sensitive floorings. And more commonly, particularly in fast track, sort of high profile construction, there's been an increased use of moisture mitigation systems, which are essentially 100% solids epoxy coatings put on brand new concrete to essentially eliminate the risk of future moisture damage to moisture sensitive floorings. Next slide. And I have a nice example kind of tying several of these products and concepts together in a recent case study I've worked on. And this particular one involves actually in a fairly old 35, I believe, year old building, actually multiple buildings that had the same problem that recently underwent some pretty severe remodeling and tenant improvements under the new ownership. These are single-story buildings, all of which exhibited commercial buildings, all of which exhibited localized but widespread, but yet widespread nature failures of vinyl flooring, and which, as you can see, manifested in the form of blistering and bubbling, sort of along in this particular case, vinyl composition tile edges. There was other areas with sheet vinyl flooring that exhibited similar issues. Upon removal of the flooring, we determined extremely high moisture content in the underlying concrete slab, and evidence of re-emulsification of the adhesive around the perimeter of the tile, as well as evidence of mineral deposits accumulating in the concrete surface. And what we had determined, this was obviously quite a head scratcher for everyone, including people like myself who have seen a lot of flooring failures. What could possibly explain such a localized nature of these failures? And as it turned out, the contractor who performed the tenant improvement work went ahead and cut trenches in the concrete slab in an effort to install plumbing for new bathrooms, new facilities, as well as some seismic retrofit work. And in the process of that, disrupted the underlying moisture vapor retarder, as you can see in the photo on the right. From a core hole, we extracted right at the interface of the damaged and undamaged area. And so in areas of these, the areas that you can see that corresponded to moisture damage were underlain by new concrete infill slab that was installed to just fill those trench locations. And right below that slab, there was no longer a moisture vapor retardant. It sort of underscores the importance of installing it. Next slide, Mike. Now, switching gears to tile installation. Again, very, very common and broad use in terms of polymer additives in the thin-set mortars. You may have heard of latex modified thin-sets are extremely popular particularly in commercial installations. Waterproofing membranes, either liquid applied or sheet membranes. Sheet membranes also, of course, incorporating polymer-based adhesives. Various uncoupling membranes designed to accommodate movement of tile floor relative to the underlying concrete slab and vice versa. And crack isolation membranes designed to accommodate movement of at crack and joint locations in underlying concrete. Next slide. Here's an example of sort of an unfortunate physical interaction between polymers and cementitious materials in tile installation. And this unfortunately affected literally hundreds and hundreds of bathrooms, obviously in a commercial setting. And in this particular case, the tile assembly consisted of ceramic tile, fairly thick layer of a tile thin-set mortar installed on top of a sheet waterproofing membrane, adhered, as you can see, with an adhesive to an underlying gypsum backer board. And in many locations, the condition you see on the lower left was fairly common. It was an extreme amount of bowing of the entire tile assembly, accompanied by closely spaced craze cracks on the tile surface. And what we discovered in this case is that the relatively thick layer of the tile thin-set mortar, cementitious product, resulted in sort of this bowing or curvature that unfortunately was it was such a high level of stress that the underlying waterproofing membrane adhesive was unable to restrain or accommodate. I have another example. I think we have a couple more minutes. somewhat similar, but in a way completely different instance of also kind of physical interaction between polymer-based materials in tile installation and the cementitious materials. In this particular case, we're looking at a high-end apparel store and a mall, if anybody still remembers what that is. In this case, there was no cracking in the tile. That's the good news. But the tiles, individual tiles, were warping in kind of in the opposite direction to what I described in an example before. So the edges of individual tiles were lifted as opposed to the centers. The centers, in this case, remain bonded to the substrate. The edges were not, and it created a fairly unsightly appearance, especially given the location and the fact that it was a brand new remodel project. Next slide. We don't always have the luxury of being able to compare sort of good and bad areas, but in this particular case, we did. What we discovered is that there was a very clear difference in terms of installation components in the areas exhibiting failures. And those areas apparently or reportedly included locations where there were underlying cracks in the concrete slabs or elevated decks. In an effort in which the contractor tried to mitigate the presence of those cracks with installation of a crack isolation membrane right below the tensant mortar. And the failure mechanism is really kind of a perfect storm of three different things happening. We have, as it turned out, we had a tensant mortar that was, for whatever reason, required a fairly high amount of water to be added during mixing. That water from mixing was apparently capable of saturating fairly high absorption tile installed on top of it, which allowed for warpage of the tile. And because the underlying crack isolation membrane underneath the tensant mortar was a peel and stick product that didn't have as you could probably guess, a very strong adhesion to the substrate, that allowed for debonding of the membrane along the edges. And next slide, Mike. Okay, well, I'd like to transfer over back to Erin. Erin, I think you're on mute.
Did we lose Erin?
And some of the different places you see them in construction and building. So
Erin, can you hear us?
appreciate your attention today.
Erin, we
I'm
lost you
sorry.
for a brief moment. We didn't hear most of that. Sorry.
Erin, Mike, Matt, that was excellent. Thank you so much for your time today. Does anyone have any questions for our speakers before we sign off? I'm not seeing any, but I'm sure if after this presentation, if people have questions, they'll certainly follow up. Erin, Mike, Matt, thank you again for your time today. We really do appreciate it. And hopefully we'll look forward to working together on some of these cases moving forward.
Sounds good. Thank you for the invitation.
Thank you. Have a good day, everybody.
Hey guys, stay safe out there.